Hello everyone, this is Group 14's Critical Design Review, and we're doing a monkey tracker senior design. Our group consists of 3 electrical engineers and 1 computer engineering. So let's get to it.
The project our group was tasked with was to track an endangered monkey species called the corn-top tamarin. Right now, the researchers are using VHF telemetry to track this monkey, which is like using a metal detector on a beach. So we were tasked with finding a better way to track these monkeys and to limit human interaction with these monkeys.
Our goals and objectives include having the capacity to store live data and packets of information for both the tracker and the base station, as well as having accuracy of the location within 10 to 15 meters, a GIS software for the general area of the track groups, which is the CS responsibility, having a widespread coverage of 2 to 10 hectares of habitat, and of course, a long battery life. The specifications of this senior design project requires that the weight of the tracker cannot exceed past 3% of the monkey's body weight via 14.5 grams, which will impede the monkey's mobility and daily life. The tracker must have a capacity to have a service life of 1 year, and the base station cannot exceed past 4.5 kilograms. This slide visually represents how our group subdivided the workload and interconnections of our tracker/base station's research and development that was planned last semester. This implementation greatly reduces the amount of work distributed between each members. To accomplish the goals and objectives of our senior design, we decided to implement a GPS tracker that will transmit data via coordinates and can be received to our base station. Adafruit's GPS breakout provided the foundations on how to program the GPS along with the sample code to test its functionality. There were several parameters to deciding what GPS module to choose from, such as the active and sleep mode and scheduling for transmission, the operating conditions, acquisition time, and especially sensitivity. Then we had to decide on the right antenna to choose from and deal with the weight constraints. With that in mind, we chose the ORG 1411 as it was the most cost effective GPS unit and became our main implementation with successful results.
The methods of communication we have come up with to send the GPS coordinate of the monkey tracker to the base station, which would be sent to a website the researchers could access. We came up with two different methods, one being Bluetooth and the other being a network of radio transceivers using LoRa. For the Bluetooth implementation that we tried out, we found out that Bluetooth was not a good way to track the monkeys because Bluetooth did not reach the meters goal we wanted. Instead, it reached about 25 meters and not the projected goal of 100 meters. It needed to reach to be competitive with the radio implementation. As you can see in the picture where it broke up around negative 85 dBm. In real life, this was about like 25 meters away from the Bluetooth beacon. From this, we would need a lot more base stations to make this method work, and which meant that we would need a lot more money to make this implementation viable compared to radio. The other problem with Bluetooth was that we would need to make a Bluetooth mesh network to connect the trackers and base stations together. To get a Bluetooth mesh network to work, we would have to put a lot of time in to get it to work seamlessly. And since we didn't have enough time left to reliably say that we could get it working without any issues was a big uncertainty. The reason why this is a problem is because the radio implementation was working seamlessly in the testing we did outside. From these downsides, we decided as a team to go with the radio implementation instead of the Bluetooth implementation. The method we decided as a group to go with is using LoRa radio transceivers because it hit our goal of 400 meters. And also, the other major benefit with using LoRa technology is that there's free to use frequency bands. And with using other devices, you might have to purchase a license from the government, which is very costly. And the other major benefit with using this method was that it's more cost effective than Bluetooth because of we only need one base station instead of a lot more with Bluetooth. The other benefit is that we hit the range of 400 meters. That was our goal the researchers gave us. And the other main benefit was that there's a lot of open source libraries out there to code a device using LoRa.
In decision between the ATSAM21 and the MSP430, we have chosen the Arduino Uno as the main architecture for implementing both the tracker and base station. Most of the modules we've chosen provide sample codes that are programmed using Arduino IDE, such as the Adafruit's LoRa M0 Feather, the SIM7600 Arduino Shield, and the GPS Breakout. This microcontroller is also most familiar to our group, has accessible libraries for the GPSM radio modules, and ideal for our featherweight specifications. With these in mind, it outweighs the MSP 430 route, even though it consumes less power than the ASM21 from its datasheet.
We have three requirements from our customer Dr. Ann Savage for the base station system: long service life, budget, and reasonable weight and size. The customer requires a reasonable weight and size because the base station will be strapped near the top of the trees or in the upper canopy for good sunlight exposure and connectivity to both the backpacks and the closest cellular tower in the area. If the base station is heavy, installation and serviceability becomes difficult, and the risk of the straps breaking or tree giving way over time only increases as we pile on more weight onto our base station design. Budget-wise, for the full package of 6 trackers and 1 base station, the cost must be less than $2,400. This is the cost of the current system being used. According to our current cost analysis involving cellular data plan payments and estimations for the cost of all 6 backpacks, we are limited to around $500 for the base station. The motivation behind the long service life requirement is that Dr. Savage's group can only service the devices annually at most. The base station therefore must be able to sustain itself with the power and remain operational through a forest environment's humidity, temperature, bugs, weather, etc. Functionality-wise, it must relay all 6 backpack transmitters' GPS data to the customer consistently throughout its service. Here we have an image of all of the base station's hardware connected and functioning. Just like in the tracker system, the base station will utilize an RFM95 LoRa transceiver. This is because of its success in penetrating through vegetation during testing and its performance at 450 meters. Using this transceiver as a single channel receiver limits the base station to listening to only one backpack at a time, but due to power budgeting with the tracker and consequently the hard limit on the transmissions we can send per day for each backpack, a single channel receiver is appropriate for our purposes and significantly cheaper than the multi-channel options. The Arduino Uno development board was initially chosen for convenience because we had an unused board and were familiar with the Arduino IDE. When researching for a cellular module, we conveniently found DF Robot's SIM7600 Shield compatible with the Arduino Uno. This Shield is 4G compatible and has supporting add-command manuals for debugging through a serial monitor. Unlike the initially tested 2G SIM800L cellular module, this Shield can connect to the internet, automatically sets the SIM card's APN if no password is required, and has quicker network acquisition times due to the overall better coverage of 4G. Connection to the internet introduces a new form of data transfer instead of just using SMS. We desired a SIM card that can operate in both the US for our testing purposes and in Colombia for service. Hologram SIM works with many cellular providers to offer a global Internet of Things SIM card. Using add commands and testing in different locations, we have seen it connect to AT&T and T-Mobile.
This slide refers to some of the major power draws we referred from the datasheet to be implemented to our base station and tracker. Although it doesn't represent the actual power consumption of these systems, it helps us consider the necessary capacity of the battery and weight for the battery we will use, especially for the tracker. We've chosen the LiPo batteries as our main source of power because it has a higher energy density than most of the battery options. It also has a built-in protection circuit, and it also has a rechargeable feature. When implementing the LiPo batteries, we need to be mindful that the battery voltage must be within 2.7 volts to 4.2 volts for functionality. In consideration of the power consumptions from the previous slide, we have chosen a 400 milliamp hour for the tracker, a 3.7 amp hour capacity for the Arduino Uno, and a 4.5 amp hour capacity for the GSM Shield. For solar panels, we've chosen these polycrystalline solar panels as it provides 5 volts with a max current of 0.5 amps, which is sufficient for charging the LiPo batteries. With that, it provides a solid solar efficiency of 17%, has a sturdy frame, and weatherproof. The solar panels are also within the solar charger's rated specifications to prevent any damages of the charger itself. The most attractive reason why we chose the panels is how readily available they are to purchase within a short period of time. The DF Robot Solar Power Manager was the best choice for regulating the solar power input from the panel to charge the LiPo battery, with its features including protection circuits to prevent damage to the base station and implementing an MPPT algorithm to maximize solar conversion. This solar charger will provide an output of 5 volts and a max current of 1 amp to the Arduino Uno for the base station. This was the only solar charger that provided low cost, fit the necessary specifications, and availability from vendors. This DC-DC converter was chosen to regulate and monitor the voltages and current of the SIM7600 module, with the added feature of the LED display. We were concerned that the SIM7600 has a max current of 2 amps, which exceeds the solar charger's specifications previously mentioned. However, looking at the solar charger schematics, we can change its DC-DC converter values such that we can accommodate the voltages and current for the SIM7600.
Here is a flowchart that roughly outlines the base station software. At the start of the code, the radio module is initialized. This uses SPI communication to the Arduino Uno. Shortly after, the cell module is initialized and communicates through UART to the Arduino Uno. The cell module is set to idle mode because it's not needed until a transmission has been received. The radio module is set to query for incoming radio transmissions from the backpacks and runs 24/7 unless a transmission is being processed by the base station. Once a transmission has been detected, the code breaks out of the radio transmission loop, the string is stored in the Arduino's ROM, and the radio module is set to sleep. The cell module wakes up through an add command, and after checking a few conditionals, the Arduino Uno sends a sequence of add commands to the cell module in preparation for firing off an HTTP post. The data gets posted by embedding a singular transmission string in the website's URL and executing an action add command. After the cell module is finished, the cell module is set back to idle mode, and the code jumps to querying with the radio module for transmissions.
The CS team is creating a website that will display values outputted by the hardware. We currently have two options to transfer our data to upload onto the CS team's website. The first is attempting a direct HTTPS post by having the Arduino Uno send add commands to the cellular module, and the second is sending an SMS to the hologram cloud and using their data routing service, which uses a webhook application, to post the data contained in the SMS to their website. The CS team must register the base station as a device on their stack, create the necessary API endpoints and query for the post request by the base station, parse the data package posted by the base station, and display the organized values of every transmission. This includes values like latitude, longitude, time of day, date, tracker tag, etc. The mechanical engineering team has designs for the backpack, and they are basing it off of the older tracker that Dr. Ann Savage is currently using, which is displayed on the left. On the right is the ME team's current draft of the backpack housing with the dimensions 60 by 37 by 17 millimeters, which is subject to change. For the housing of the base station, we are considering a shoebox for size and mounting the solar panels in a triangular rooftop fashion. The ME team is tasked with creating the housings for both the backpack and the base station systems, protecting the electrical components without hindering the signals, installation considerations, for example, a strap for the backpack and base station, waterproofing, tamper-proofing, heat flow dissipation considerations, and more.
Starting with an overview of what my section will be looking like, our group has two different PCBs, which are the GPS breakout and the full tracker PCB. The purpose of the breakout is to isolate the GPS from the rest of the system because it was the one component we did not get to test directly in our test kit phase. This way we can more directly troubleshoot just this component. The tracker, of course, is our fully integrated design and incorporates the GPS within it on the same PCB as the rest of the project. The structure of this section will be schematics for the GPS breakout, followed by schematics for the tracker, where we will look at parts and interconnections. followed by the board section, where we will mostly be looking at interesting trace, pore, and layout considerations, again for the breakout and tracker. Because the GPS tracker is so unchanged in the tracker design, these duplicitous considerations will be glossed when they come up the second time around. Without further ado, let's hop right in with the GPS breakout schematic overview. Taking a look at the GPS schematic, I can say that the ORG1411 GPS is actually a 1.8 logic chip that can tolerate up to 3.6 volts. This means that the ORG1411 can take orders from the microcontroller, but can't necessarily talk back. In order to make that possible, we included the Texas Instruments level shifter by the name of the SN74, etc., which bumps up the 1.8 GPS output to 3.3 volts. Beyond this, the reference design provided by the company which makes the GPS recommended the inclusion of EMI filter capacitors. The precise version they advised was not in stock, so we swapped them for what appeared to be equal alternatives. The final point to look at is the particular resistor setup shown here correlates to setting the GPS module into UART only. The module can run in I2C, however this would require a different setup. Moving on to the tracker PCB, we can see the buck converter in the upper right, the reset button immediately to the right of that, the LiPo charge controller to the far upper right, the microcontroller below the charge controller, the radio in the middle, the GPS to the far lower left, and the micro USB just above the GPS. Diving into the power circuitry first, we have the two main ICs, the buck and the LiPo controller. The buck converter's job is to moderate our power inputs from the USB or the LiPo down to a system-safe 3.3 volts. The USB can output up to 5 volts, bumped to 5.2 for safety, and the battery, if fully charged, can be outputting up to 4.2 volts. The regulator is capable of dropping this to 3.3 volts, with up to 500 milliamps of current to feed the system. The buck converter also has the charge protection diode attached to it to make sure we never have an accident where the USB is directly charging the battery. To the right of the buck converter, we can see the LiPo charge controller, whose job it is to take the micro USB power input and regulate it to levels healthy for the battery to charge off of. The configuration resistor is used to modulate the current flow and is presently set to the healthy and low 100 milliamp charge rate. The GPS section of the schematic is the same as we have looked at previously. Moving on to the microcontroller, we can see its numerous data line connections with peripheral modules. We can also see the crystal oscillator used for precision timing to the upper left with its associated external capacitors. To the right, we can also see the battery divider used to monitor the battery state of the system. This implementation is not ideal because it always results in a leakage current from the battery to create the monitorable voltage for the battery divider. However, with all the other components on the board, I didn't want to risk complicating things further with an additional on-off MOSFET to choke out the battery divider line. This would definitely be an improvement point in a final design. Moving on to the radio module, we can see the antenna header pin connection for the 900 MHz spring antenna also shown. We can also see that we found most of the pins unneeded when doing kit testing, so several of the configuration pins have been left alone. Starting our discussion of the boards, the most interesting feature by far is the GPS and its related board layout specifications. The manual from the GPS said that it required a top copper keep-out area around the module, which we can see by the bottom layer peeking through the top layer to the right. It also specified that the module requires what the manufacturer is calling a ground paddle, which must be connected to an uninterrupted ground layer of at least 13 mm by 13 mm. This ground paddle must also have a hole cut into it at a precise location to avoid interfering with an antenna pin. Moving on to the tracker PCB board, we can see the GPS very minimally changed at the bottom of the board. Centrally on the board is the microcontroller. The top of the board is the radio module with its antenna header mounted just at the edge of the board. Moving to the right-hand side of the board and progressing downwards, we first run into the battery connector, followed by the LiPo charger circuitry. After this, we have the micro USB and the reset button just to the left of the micro USB. The bottom consists of the buck converter. The USB is sandwiched the way it is because this means it has a short path to the power circuitry and to the ATSAM D21, which should help ensure insubstantial data line noise. On a related note, the radio and GPS were kept apart because the radio might have degradative effects on GPS performance. Similar to the USB data lines, the SWDIO and SWCLK lines we will be using to bootload the microcontroller also have as direct a signal path as possible to prevent noise. One mistake I made on the PCB was forgetting to thicken one PCB trace segment going from the converter resistor to the converter capacitor. Thankfully, when checking PCB trace calculator, the thickness for an external trace recommended for 0.5 amps is 9 mils of thickness. The standard eagle thickness is 6 mils, which is less. However, the 0.5 should only occur during maximum draw. Putting a more reasonable 0.4 amps results in 6.68 mil, which is hardly more than what has already been placed. This slide also has images for the more interesting parts which will be mounted to the tracker. Final slide here. This slide has a picture of the manufactured tracker and breakout PCBs. We in fact just recently got a pair returned to us from QMS who did some partial assembly for us, so now we have to place the remaining parts on those boards. I don't have a picture for you of those partially completed boards though. This concludes the schematics and board overview section.
For programming the tracker, the main language we use was Arduino. Within Arduino, there's a lot of inbuilt libraries that are free and open source. The reason why this matters to us is because we have two main components, the radio transceiver and the SAMD21 in the tracker. And these components need these libraries to be used. Without these libraries, it'd be almost impossible to program the tracker. In this slide, we're going to be mainly talking about the SAMD21. Within this chip, there's a thing called sleep mode. And the sleep mode, we're mainly going to be using it standby mode. Within idle mode, it just turns off half the clocks, which is not very useful for our device, but standby mode allows us to turn off almost all the clocks except for one. So the clock we're not turning off is the external RTC clock. And the reason why we're using an external RTC clock is it has a lower time drift than the internal RTC clock that the SAMD21 uses in standby mode. So what would happen is the CPU is going to get waked up by the external RTC clock, and from that signal it's going to send a signal, wake up the GPS. GPS is going to get the information. Then with that information, the CPU is going to send that to the radio transceiver. Radio transceiver sends that to base station. After all that's done, what's going to happen is we're going to go back into standby mode and wait until the next signal from the external clock. For scheduling tracker, we're going to have 6 trackers for one base station. We're trying to make it so that 2 trackers don't speak to the same base station at the same time. Because when that happens, we're going to have modified information from the tracker, or we're just not even going to pick up one tracker's information. That's the reason why we have an hour difference between each tracker when they send that information to the base station. And the reason why we picked 1 hour is because the time drift of our external RTC clock for our tracker is about 25 minutes, meaning that the first tracker could start speaking at 6:55 a.m. and the second tracker could start speaking at 7:05 a.m. And so that's the reason why we have that hour difference. Another thing is we only picked active hours where the monkeys are not sleeping, because that's what the researchers want us to do.
The main difficulty for this project was finding the right modules and electrical components, which was difficult enough due to the shortages of units and the insane weight constraint, which limited our resources. However, after dealing with it, we finally designed our PCB for the GPS tracker and successfully sent an SMS message from the base station with some complications with the SIM card holder. Here is our current progress distribution, where it includes the mechanical engineer's enclosures, the CS websites and parsing research, both the hardware and software of the tracker and base station. From this chart, our overall progress is roughly 62% complete, which is relatively on mark, but we need to ramp up our design's completion rather soon. After recapping last semester's progress, the plan going forward includes soldering and assembling our PCB tracker. Then test the base station and tracker's functionality over the course of 12 hours to determine power consumptions and connectivity. And finally, collaborate with our interdisciplinary groups regarding parsing data to the website and the enclosures for the tracker and base stations for integrity and weight considerations. This concludes our critical design presentation. Thank you for listening.